Hi, everybody, and welcome to another session on the first day of the MRI Together conference. The title of this session is Acquisition from Paper to Scanner. And my name is Nicolas Stikov. I am a professor at École Polytechnique and the Montreal Heart Institute, and it is 3 p.m. where I'm at. I just came back from another event in Montreal called Neuroimaging in Montreal. I know a couple of people from there will also be joining us, and I'm very happy to be joined here by 4 researchers who will be talking on the topic of going from a PDF to the scanner. We will kick things off with Gehua Tong from Columbia University, and she will speak about a framework for validating open source pulse sequences. We will proceed with Jon-Fredrik Nielsen from the University of Michigan, talking about vendor-agnostic MRI pulse sequence programming. And then we'll have a short discussion, and then we'll continue with Agah Karakuzu from my lab, from Polytechnique, on improving inter-vendor reproducibility of quantitative MRI. And finally, we will finish with Nora-Josefin Breutigam from the Fraunhofer Institute in Germany, and she will talk about the evolution of vendor-independent MRI frameworks. So just a couple of announcements before we start. I would like to remind you that the conference is recorded, and it is also broadcasted live. If anybody wants to have access to the transcriptions, they are available on YouTube. And also, please be aware of the code of conduct, which you can find on the MRI Together webpage. And finally, regarding the Q&As, we would love to get participation. We would love to get a discussion going. And just a clarification that we would like you to ask the questions in the Q&A box and not in the chat. And this is maybe a little bit confusing because the Q&A box has a little question mark in it. And this will allow us to see it, and also it will allow you to upvote the questions so that we can ask the ones that are the most popular. So with that being said, I think we are ready to start. And I would like to invite Gehua Tong to share her screen and start the presentation.
Hello, everyone. First of all, thanks for the invitation for the talk. My name is Gehua Tong. I am a PhD student in the Department of Biomedical Engineering at Columbia University and also a member of the Columbia MR Research Center. And today I'll talk about a framework for validating open source pulse sequences. So the talk is divided to 3 parts. The first part, I'll talk about open source sequences and the need for validation, followed by our preliminary framework and as a first step of documenting and sharing the sequences, and we demonstrated using 2 basic sequences. And lastly, I'll talk about some new developments since the publication of the paper on testing UT sequences, 5 UT sequences across 3 sites. So the motivation is that, and it's something we're really excited about, is we have been seeing development of these open source MR sequence standards, formats, and platforms. And they help 3 aspects. One is having a way of replicating methods across site as soon as possible. Second is performing multi-site studies so that to standardize the sequences as much as possible and match the waveforms so that the data can be comparable as well. And lastly, to have these data or these sequences as data in publicly shared so that they can contribute to the goal of accessible MR and being able to distribute these methods across the world. And we have some challenges as well. The first one being that there's no standard process for saying whether a sequence reaches some standard of quality, or even saying what comprises a sequence. And also there are multiple formats, each of which has their different philosophy and flexibility in terms of how much the waveforms could change and how things constrain each other. And lastly, validation on multiple vendor platforms could be challenging due to format translations. And our proposed first step for this is to have a framework that puts the responsibility on the developer to perform test experiments and share these along with sequence files, documentations, code, etc. And we provide a developer form for documentation and a user form for feedback. So we gathered some information about different open source pulse sequence formats, and there has been many, and they can be mainly distinguished by the language written in their formats, whether they have a one file representation or multiple files, or is it a program. The number of vendors supported directly, so those come with the interpreters already, and also the number of vendors via an extra step or extra translation. And some other aspect we are interested in are simulation, which can help save some time to have to run like a test simulation before going to the scanner, having a GUI for designing sequences, and also importantly having the reconstruction included, as we know many advanced methods contain advanced reconstruction methods that are required to get to transform the data into images. And in this lit review, we found that there are two ways of looking at the sequence, one of which is probably more conceptual and represents the sequence as a tree of nodes, some of which can be loops. And the different elements or different nodes on this tree could be related to each other through parameter constraints. And the pros for this is very obvious in that we have this inherent structure that kind of adds as a safety layer of ensuring the sequence works and making them flexible for different system limits. The cons or the things I could think of are that if we want to change one part of the sequence, it tends to affect other parts as well. And it does require a step to unroll the structure to see the actual waveforms. And in bottom-up representations, the sequence is broken into multiple blocks, one following the other. And they don't have inherent constraints on each other, so that you could change one any element in one block independently of each others. But the disadvantage of this format is that it's less flexible, and once you have the sequence, although it's deterministic already, it has problems adapting to different scenarios and especially different vendors, and reconstruction usually requires extra information data. So in the framework, we don't require sequences to be one format or the other, and we love to see it being used and adapted over time to suit different formats. But basically, the developers implement the sequence, they validate it with test experiments, document the results, and also conduct some quality tests and calculate some metrics. And lastly, they share it as a package that includes, first of all, a documentation form, and also all the associated data that the documentation form links to. The users on the bottom would find the sequence somewhere, either directly by contacting the developers or through a public platform, test it locally, and report back any issue or fixes through a user form or a report form, so that the sequences can evolve over time to adapt to different sites. To demonstrate this, we implemented two pulse sequences in the PyPulseSeq with the PyPulseSeq library as Python functions that take certain sequence parameters, and tested them for regular imaging and mapping as well. So they were ISE and TSE used for qualitative or T1 and T2 mapping. So the sequence waveforms are shown here, and those were directly read from the PulseSeq files. But before going on to scanner, we did some simulation with the PulseSeq files. We used the virtual scanner block simulator, which we developed, to simulate the PulseSeq file directly using one of the included numerical phantoms. Oh, actually three of them: a T1 array, a T2 array, and a grid plane. And parameters are listed here. I won't go through them too much in detail, but basically we see that this simulator could, having the simulation process could show you that there's not some, it kind of serves as a sanity check. There's not some low-level mistake in the sequences themselves. And you could encode geometry as well as relative contrast. And it serves as an assurance before you go on the scanner. One thing to notice that there are some limits on the phantom resolution because of the speed of the simulator. So the grid phantom on B with the irises showing a lot of artifacts. So after we've done simulation, we can move on to the actual acquisition. For this, we use for qualitative experiments, we use the ACR phantom. And for quantitative, we use the SMR and NIS phantom. For the ACR, we acquired the standard planes and with matched geometrical parameters so that we could conduct the standard test, which were designed for hardware testing, but we kind of repurposed it here to show that the sequences, to assess the quality of the sequences. And for quantitative, we used the T1 and T2 arrays and conducted mapping on them. The experiments are shown in a table. The main experiments were conducted on a Siemens 3T Prisma Fit scanner with a 20-channel head coil and a pulse-seq interpreter. In addition to the PyPulse-seq sequences, there was also a matched vendor sequences that we tried to make the parameters the same wherever we could on the console. And the varying TI as well as TE for the mapping experiments are shown below the table. Here are the results of the qualitative experiments showing the PyPulse-seq images, vendor images, and the difference after normalization. For PyPulse-seq, so overall, you can see that they encode, the overall image quality is not that different, but there is a slight contrast shift and especially towards the center of the phantom here. So we try to assess this more quantitatively by computing PSNR and SSIM for each slice versus the vendor. And overall, the match is not perfect, but pretty consistent across the slices, except for slice 5, which you can see here is this grid that tends to generate more artifact, and even a small shift could produce some major differences, as you can see in this slice in F. So these are the metrics we propose for qualitative measurements. And I believe that this would change depending on what type of sequence you're using and what type of vendor sequence you're referencing it to. So in addition, we also conducted the ACR test. And most of the tests were passed, except for test 5, which assesses image intensity uniformity. All 4 sequences failed this test, which we mainly attribute to the fact that we used the same reconstruction process, which is a simple sum of squares from the raw data for both PulseSeq and vendor. And you can even see the uniformity is not great. So some additional reconstruction scripts might be needed for a later update. For test 7, it was the low contrast object detectability. Only the vendor TSC passed this test, but we like to note that in the actual number or the actual score generated, PyPulse-seq was better than vendor in the IRSE test. SNR diff was computed from 2 repetitions of the same sequence. And as expected, the vendor TSC does have the highest SNR, whereas for PyPulse-seq, the SNRs were pretty similar. So these metrics could potentially help a user to know what type of sequence or what type of image quality to expect. For quantitative validation, we performed mapping on each of the ROIs of T1 and T2 arrays selected manually. And for T1, we found a R-square equal to 0.99, and for T2, 0.93. We did have to adapt slightly the mapping process for T2, in that for the spheres with longer T2, we have to reduce the number of TE used. Specifically, we cut out the lowest TEs. And the spheres do have, those spheres do have T2s from 15 milliseconds to 645 milliseconds. And the TEs used start from 7 milliseconds. So those, we did find some signal artifacts. So these are all part of the documentation. Something really important is safety. That's included as part of the framework forms. And because we want to make sure that the sequences are safe and won't cause, well, although the scanners do have a check for that, we still want to know these values for reference. So for all the sequences, we recorded the SNR whole body and head, average RF power, and PNS threshold on the vendor console. And we also utilized the SAR4seq library, it's a Python library, to calculate these the RPAR related values in the open source sequences. And overall, none of the sequences exceeded the failed the vendor safety test, and the SAR4seq library does tend to overestimate the numbers, which we think open source safety simulation aspect should be included, and we should continue to improve these and take into account more assumptions in what shape of phantom and what shape of other subject you're scanning. For PNS threshold, we did include the values for all three size orientations. These same sequences were also, at least on a script level, were also tested at the second site with our collaborators on a Siemens Era 1.5T scanner. And because of the time limits, we couldn't match all the parameters. As you can see, the TI here is a little bit different. And the contrast resulting is also different. And because of the field strength of 1.5T, we couldn't exactly compare the sequence in a very equal way. So these were mainly used as a way for them to fill out the user form and assess how helpful that is in terms of our development. So these were included as supplemental information. So for sharing and documentation, you can get started trying this framework or giving your suggestions by going to the repository linked above here. And you can start by downloading the forms from the repository and filling them as you test out the sequences in stages, starting from simulation, acquisition, to reconstruction, and post-processing, including mapping. Then, if you find any issues, then you're the developer. So if after you've done this process, you could share the form along with all the associated files in a folder so that another site may replicate this and continue to evolve the sequence and adapt it, make it more adaptable. All the data was included in a separate data article linked to this paper as well. And on the right is an example of the PDF form for the developer, but you can find both forms in this repository. Some later development on MINT sequences. So these sequences we implemented both to run some multi-site experiments and also to kind of start the idea of having replicable sequences in the musculoskeletal imaging area. 2D and 3D UTE sequences in the 4 half-pulse modes were implemented, as well as the 3D code sequence in PyPulse-seq. They were documented with the same forms and tested across 3 sites. The site information is listed in the table below. They were tested on a NIST T2 array and a bone-in pork chop. The T's achieved ranged from 189 to 859 microseconds. And they vary slightly among the vendors, among the sites, because the script tried to find the lowest T possible. And the 2D images are shown here. I guess the first thing we can notice is that the noise level is higher in the 1.5T, which is expected. And the contrast is a little bit strange, which I'll show in a later figure. But you can see that the lowest T2 spheres, which are in the middle, has high signal. So it does recover good signal from the central spheres. The pork chops, unfortunately, we couldn't standardize that across the sites, but we did look at statistics from a bone ROI as well as a muscle ROI. Here are the 3D images, which has a lower resolution due to some limits on sequence loading time. But for the contrast, you can see similar effect, except for the 3D UT half pulse, which in general tends to have some problems. The metrics are summarized in the plots here for the NIST T2 array. You can see the contrast weirdly decrease. The signal weirdly decreases as you go to longer T2s. And this, we did look at the table of the NIST array, and I concluded that the T1 arrays the T1 values do change, and the T1 values are actually shorter for the shorter T2s. So because the TR use was pretty short, I think it's about 15 milliseconds, that caused this reversal in contrast. And this is supported by the GRE curve from Vendor, which has a higher TE, and that the T is not so short to knock out the T2 effect completely. So there's a reversal of contrast around sphere 11 or 10. The 3D curves show similar trends, except it's more noisy, especially in the 3D UT half pulse. And we do see from the images that the lower resolution does cause some artifacts that could be improved. We also look at the main cylinder SNR versus the sphere 14 SNR. Sphere 14 is the one with the lowest T2 value at 5.35 millisecond. The 5.35 millisecond for 3T and 7.8 milliseconds for 1.5T, which is site 2. Overall, the SNR was increased. Well, at least for the 2D sequences, it was increased. And we see some similar challenges with the 3D UT 4.5 pulses. And the second plot shows summaries from the porcine sample or pork chop. And the bone SNR, both the bone and muscle SNR seems to be increased by the 2D sequence in site 1. And the CNR had some more challenges, whereas we see a high CNR achieved by the 3D pulses in sites 2 and 3, but a reversed contrast in 1. So we would doubt that the bone SNR values would be valid because there could be some partial volume effects. The bone versus muscle signal ratio is the contrast we were very interested in looking at. And the UT sequences, the 2D sequences overall increased this ratio. And this effect could be further explored by conducting more experiments and making sure the ROIs are bigger. So these are some preliminary results from our testing. And obviously there's a lot to improve in image quality consistency and in matching the parameters as well. And for matching to the vendor waveforms, they're unknown. So the goal is not necessarily to match it exactly, but to use it as a base contrast reference. And the between sites differences in field strength and hardware limits and how the sequence script addresses those differences is an important topic for further research. Some of our further steps include validating the sequence with multiple vendors, which, as you can see, we couldn't do here due to some sequence translation issues. Applying the framework to other sequence formats that have different philosophies would be interesting. And also to help establish a platform for sharing those sequences so that they can evolve on multiple sites. And lastly, I'll just spend a little bit of time talking about Virtual Scanner, which is our exciting project on open source sequence development, in that we have simulation, reconstruction, and analysis pipeline, as well as includes basic sequences and 2D or 3D phantoms. So this has mainly 4 aspects to it. 1.0 of the Virtual Scanner includes it's a training console for emerging technicians so that they can get used to the MRI acquisition process before they go to an actual scanner. The digital twin concept is supported by our simulation with PulseSeq files using hardware maps so that the state of the scanner could be monitored and included in simulation to see if the PulseSeq works well with it. the virtual scanner games is an effort of developing these web browser GUIs that simulates and explains MR physics concepts and expand them to a wider audience, including high school students. And one of the two modes of this would be connected to a hardware, an open source instructional scanner, so that we can run PulseSeq files on the scanner, both for use in the games so that students can acquire images, and also in general on open software for accessible MR. So this is more future or planned development. And at last, I'd love to thank for the support from the Columbia MR Research Center and the Zuckerman Imaging Platform, as well as contributions from my PI's advisors, Dr. Saran Jitanath and Dr. John Thomas Long Jr., and my lab mates. And lastly, thanks to all of you for listening. And please let me know if you have any questions about the framework or about virtual scanner. And that's it.
Excellent. Thank you very much for this exciting presentation. And we will continue to hear about vendor neutrality from Jon-Fredrik Nielsen from the University of Michigan, who had some audiovisual problems. So it looks like we're all good now, right?
You hear me now?
Yes, excellent.
Okay. Better share my screen. You guys see my slides there?
Yes. So feel free to start when you're ready, Jon-Fredrik.
Sorry, I was getting another message from the organizer somehow.
All right.
Okay. All right. So that message ended. So yeah, thanks so much for having me. It's really a pleasure to speak as one of the speakers in this kind of interesting session where we're trying to sort of break through and open up the scanner a bit. So I'm going to talk about more on a higher level vendor-agnostic sequence programming, and particularly the approach that we are taking that's related to the PulseSeq kind of way of thinking about things. So here's an outline. So first, I want to just briefly touch on why do we want to do vendor-agnostic programming in the first place, and perhaps why not. There are good reasons not to as well. So I thought it would be good to just recognize that. So our approach is actually based on two different file formats so that encapsulate the pulse sequence, or in principle, any pulse sequence. It's based on PulseSeq, and then the format that we call TOPI, that's more geared toward GE scanners. So I'll explain how that works. And then in the last part, I'll show how you can go from one scanner to the other using this framework. So first, a few thoughts on why we want to do this in the first place. And so, I think there are at least two big reasons for wanting to scan at multiple sites. One is if you're doing a patient study, it gives you access to a larger patient pool. And so that allows you to study rare diseases, to ensure racial and ethnic equity, and to build databases of both normal and abnormal signal characteristics. But I think another reason, important reason for development is that at some point you'll probably want to validate your sequence or the findings on one site. And at that point, it's very valuable to do that on another site. In other words, try to assess if the findings are reproducible. Can they be reproduced on the site and by others? And so in some sense, every MRI technique may eventually require cross-vendor programming. So I hope that this motivates this a little bit. And so suppose you want to do multi-site. Why do you want to do the programming in a vendor-agnostic way? I think there are 4 good reasons that I could think of. One is to avoid duplicate efforts. So here's the typical scenario where you have some pulse sequence, and if you want to implement that on 2 different scanners, you have to use the vendor software development kit, and that can be quite a task to do that. And you end up with a proprietary file that only works on one scanner. And to do this on different scanners, it's pretty rare that one person is able to actually do that on more than one scanner because of this steep learning curve. So the basic idea behind PulseSeq is to encapsulate the sequence in a sequence definition file that can then be sent to different scanners. So that's kind of the idea. So the sequence programmer only needs to define the sequence once, and that should, in principle, work on multiple scanners. So it saves time. Another important reason, a practical reason, is that it minimizes disruptions caused by scanner software upgrades. So here's the typical scenario where, let's say, you've implemented your favorite sequence using the vendor SDK, and then 12 months later, the scanner is upgraded, and then you need to update every sequence that you work with, and so forth. And so with the vendor-agnostic approach, you just define the sequence once, and every 12 months, let's say, you need to recompile the interpreter, and that will be, given to you by the development team that develops the interpreter, and you just have to do that once, and that's universal. Like the sequence descriptions don't change over time. Another important reason. Another thing is that it enables kind of a complete open source workflow from acquisition to reconstruction, as described in this paper by Feldman. And so the idea here is basically to utilize not just open source acquisition, but also open source image reconstruction and analysis. So in this way, you can go all the way from an open and non-proprietary description of the sequence encapsulated in the file to data acquisition. Then you can save that if you like in the ISMRM RD or MRD data format. And then in this paper, Martin basically created the header entirely from the PulseSeq file. So the MRD file is basically just used as a container for the raw data from the scanner, and then you can use that in the reconstruction. So that's another compelling reason, I think. So it opens up kind of the entire workflow. And another reason, which is mainly the main motivation for why I think we started this in the first place, was actually to do rapid prototyping and to share sequences that we developed. So with this setup, we can program the sequence using interpreted languages, which is much easier, or can be much easier, than using the vendor SDK. And the code can be very minimal. I'll show some examples. And it can be freely shared. It's open. It doesn't contain any proprietary information. And importantly, this allows you to analyze the sequence offline. So you can simulate the sequence, for example, using the GEMRIS software. You can inspect, things like the RF and gradient limits, ensuring that, it looks the way that you intend. You can do things like check the peripheral nerve stimulation using models that are implemented in MATLAB on both the GE and Siemens scanners, and RF and gradient power and so forth. So that's another, I think, important reason why this is useful. There are good reasons to not do it, and I think that's why this motivates, I think, other sort of approaches that are somewhat orthogonal, I think, to sort of the PulseSeq way of looking at things, and I think that's really great. And so there's some obvious ones. If you program the sequence using the vendor SDK, you can use the vendor's user interface and entire workflow for things like slice planning. And you can leverage the vendor's image reconstruction and analysis pipeline potentially. Of course, the vendor provides application support in many cases. And you can enjoy the benefits of an existing user community that's existing within each vendor. For example, work in progress sequences. So those are some very good reasons to continue doing that. So perhaps there will be some symbiotic relationship between the kind of approach that I'm talking about and the existing sort of workflow, vendor-dependent workflow. So this is some thoughts. So now I'll describe the two file formats that we've come up with and that kind of work together, PulseSeq and TAPI. So the basic idea behind both is, as I said, to encapsulate the pulse sequence in a sequence specification file. So if this can be a text file, it can be human readable or not. But essentially, it enforces a strict separation between the design of the sequence, which is done by the pulse programmer basically once, and the application of that file, of that sequence. And by application, I mean it could be, of course, it could be played out on a scanner using each scanner's interpreter, or you may want to do something else with it, calculate the PNS, as I said, or SAR, as we just heard, using SAR4-seq, or you can perhaps simulate the sequence and so forth. And so this strict separation is perhaps the most simplest way to set this up. So the focus here is on simplicity, and then encapsulating the sequence in a way that can be ported across different applications and use cases. And so there are two file formats that I'm going to talk about, PulseSeq and TOPI. So PulseSeq is an open pulse sequence description standard that's becoming pretty well known now and really starting to pick up steam. Siemens basically has essentially a native PulseSeq interpreter, so that works very well. For GE scanners, which we use the TOPI interpreter. So TOPI is a sort of a file format that's somewhat similar to PulseSeq. It basically encapsulates similar kinds of information. The file format was developed sort of with the GE scanner in mind, so that's why the structure is a bit different, and I'll talk about that. But because they're basically describing the same thing, you can convert to and from the TOPI and PulseSeq formats. Sorry, I again heard some organizer message in the background there. So that's the idea. So let me start by briefly describing the PulseSeq file format. So the basic idea that's important to know is that it's based on concatenation of non-overlapping blocks. So in this plot here, the blocks are separated by these red vertical dotted lines. So in this example, you would have an RF excitation block. So this would have an RF pulse and then a slice select gradient. And then the next block has the slice refocusing gradient and so forth, and the phasing cogradients in this case, and the readout dephaser gradient. And yeah, you can see how you can basically stitch together these blocks. They're non-overlapping. They don't need to end at zero gradient, so that gives you quite a bit of flexibility. And that is somewhat different from the TOPI way of looking at things, and that I'll describe later. But that's the basic idea. So you have to think of your sequence in terms of these non-overlapping blocks. And so here's the look at what the PulseSeq file actually looks like. So each row here is basically the execution of one block or one event. And so you start out, let's say, with an RF event, and then you would go and pick out from somewhere else in the file the RF shape, and also the RF amplitude and phase and so forth. And then there may or may not be gradients associated with that. So in this case, there's a Z gradient, so that would correspond to that first block that we just looked at, and so forth. So in this way, the sequence is described as a sequential execution of these blocks, and there's no concept of a loop or any other kind of dependencies here. It's fairly general. So all the sequence information is contained in this way. So other parts of the PulseSeq file will have the actual gradient and RF waveform shapes. And regarding the gradient shapes, they can either be arbitrary shapes or it also has a trapezoid kind of object or a specification that you can use in your sequence. That's the basic file format. And when you actually program the PulseSeq file, you wouldn't edit that file by hand. You would use, for example, the quote-unquote official PulseSeq MATLAB library, so shown here. So here on the right is essentially the entire code for generating a 2D gradient echo scan. So first you would define the system properties, in this case, the maximum gradient and the maximum slew rate, for example. And then you would create this sequence object using the MR toolbox. And so, this toolbox comes with various helper functions. Here's one that makes a sync pulse. You could create that RF shape in any other way, and then create a PulseSeq object out of that. You don't have to use, those built-in functions, so it's entirely flexible. And there's another function here that lets you make a trapezoid. Again, you could make an arbitrary gradient any way you want and put that into the object. But this particular function uses, these trapezoid objects because they're pretty sparse. And then there are some timing calculations. And then in the scan loop, where you define the scan loop, this is a 2D gradient echo, you basically add these blocks. So you start by adding an RF excitation block consisting of an RF pulse and a slice-like gradient. And then you generate the phasing code gradient object, GUI pre. Then you add that to that next block. So that would be like essentially a dephasing block. Then there's a delay, and then a data acquisition, and then another delay. So this, and then you finally write it to a seq file. So that's basically it. And then you export that seq file to the scanner. So that's the basic workflow of PulseSeq. And then on the scanner, there's an interpreter that you only have to compile once that loads that gre.seq file and executes it. It's pretty robust. And there are many usage examples out there. Here are just a few showing how you can use PulseSeq on a variety of different hardware and applications. So then I'll switch gears and talk about the TOPI file format that we actually use here. So we like to go from that format to PulseSeq, and I'll show you later how to do that. So let me just summarize what this file format looks like. So it builds the sequence or structures the sequence a bit differently than PulseSeq, but it essentially has the same information. So the idea here is that you divide up the sequence into these modular sequence blocks, and I like to refer to them as modules and not block, because just to avoid confusion with sort of the PulseSeq nomenclature. But the idea here is, again, to have, in this case, suppose you have an RF excitation block with some arbitrary gradients, and all the gradients and waveforms in TOPI are arbitrary. So there are no concepts of trapezoids here. And so you would encapsulate that in a file. And then the readout, in this case, a spiral in readout, or a 3D spiral in, stack of spiral in readout, would be then saved in another file and so forth. So in this way, you would define typically a small set of modules that you would play out, and they're saved in the file at full amplitude. And then in the scan loop, you simply play these out with some amplitude scaling that you specify in this file. And I'll show you how to. You wouldn't write this file by hand. You would use the TOPI MATLAB tool, as I'll show next. So that's the basic structure. So save your waveforms at full amplitude, and then in the scan loop, you simply play them out and scale them and apply frequency offsets and phase offsets as needed. So here's the workflow. So first, you would create your waveform shapes, and we don't mandate how you do that. You can do that any way you want to. You can, for example, you could use the PulseSeq MATLAB toolbox to do that, to generate your RF and gradient shapes. Once you have those shapes, you write them to these module files. So again, you specify the system hardware specs, and then you simply call this write mod function that writes your waveforms, in this case RF1 and GZ1, to a mod file. And once you have that, you can plot it. So here's a simple mod file with a slice select RF waveform. This is a minimum phase SLR pulse. The spoiler and the slice select waveform are now combined into one module, and that's it. And this also plots the PNS, by the way. So this confirms that you're not exceeding the PNS limit. So once you have that module or a set of those modules, you just have to specify the scan loop file, specify how you want to play them out, what order, and with what amplitudes. And here's one example of doing that. So you would first use this function called write to loop to initiate the scanloop.txt file. It just creates an empty scanloop.txt file. And then you specify your scan loop, and you set the amplitudes, and you use the write to loop to basically write one row of information into that scan loop file. So this is equivalent to writing one row in the PulseSeq file, essentially one block or one event. And then after excitation, we have a readout. We can update the RF pulse and update the angle and so forth. If you notice, here we can specify not just the amplitude of the gradient and the phase of the, let's say, acquisition. You can also specify the rotation, both the in-plane and 3D, although I'm not showing that here. So that's basically it. And then you finish that off by closing the file. So it's pretty similar to PulseSeq. It's essentially as compact. It's just a little bit different way of thinking about how you put together the sequence. So here's an example of this particular case. This happens to be a stack of spokes or stack of sparse sequence, and that could look something like this. If you notice, the spoke direction changes here. And the interpreter it's just like any other normal epic sequence that we can freely share to users, to other GE sites. And here's just some quick examples: 3D spiral, EPI. We can measure the spiral trajectories using a sort of a pencil beam measurement, and we see that both scanners really have excellent gradient fidelity. Here's just another example of a tailored aura pulse. Here's another example of some crazy readouts with arbitrary waveforms that we can easily play out using this setup. So then I just have a couple of minutes left. I'll just want to go through briefly how we use this setup to do cross-vendor sequence programming. So the most, at least to us, the most useful tool is going from the TOPI format to the PulseSeq file. So that's been pretty robust for us, and we were able to scan both on our GE scanners and then starting now to scan also on our Siemens scanners here at University of Michigan. So the goal here is to execute a TOPI sequence on a Siemens scanner. And to do that, you need these two toolboxes that are on GitHub, PulseGeek and TOPI itself. And again, you start by setting the system hardware limits, both for the GE scanner and the Siemens scanner. And then you just convert. It's just a one-line function call. So it's a GE to C command. So all the TOPI files, there are actually several files that are bundled into a tar file. And then you specify the name of the output file, and that's basically it. So before these are the modules of the TOPI file. So before converting to PulseSeq, this is what you have. So you have a tip-down module and a readout module. And then after converting to PulseSeq and then plotting, you end up with this. So this is a PulseSeq plot using the PulseSeq, plotting the PulseSeq file using the PulseSeq toolbox. And so you see that you have your minimum phase SLR pulse and then your spoke, your readout here. And that's pretty straightforward. So essentially, TOPI supports a subset of PulseSeq, so that's why this conversion is basically exact. And so here's an example, a recent example where Highway in our lab used this setup to program a looping star or a functional MRI sequence. This actually only contains two modules. There's a long sort of RF excitation module and then a readout module. And using this, you can do functional MRI with that using a silent acquisition. So using the setup, you have quite a bit of freedom in the types of sequences that you can program. And then you can also go the other way. You can, if you have a PulseSeq sequence, you can execute it on a GE scanner using the seek to GE command. You have to take some care because you want to define as few blocks as possible. So if you sort of naively take any PulseSeq file and straight, convert it straight to TOPI using this format, you might end up with a sequence that's too time inefficient. So for example, for EPI, that would not work too well. So anyway, so I'm out of time. So I want to acknowledge all the people that have worked on TOPI and PulseSeq and PyPulseSeq as well, as we've heard, and also other groups that we're collaborating with. So thanks very much.
Excellent. Thank you very much, Jon-Fredrik. And this wraps up the first half of the session. And we have about 10 minutes for a discussion. I would invite everybody who is on the call to join the discussion. And there is a couple of questions that were asked by Daniel. And Daniel, if you want, feel free to ask them in person. Otherwise, I will just read them. So basically, I'll start with one, but basically it flows into the other. Is there a quick way to translate a vendor sequence to the PulseSeq format? Did somebody already think about translating vendor sequence simulations results to vendor-independent format?
Oh, I am not aware. I have a feeling that someone has tried that for Siemens, but I don't remember what the status is, and I don't know how easy that would be. I think it would take some work on the G, but it might be possible. But as I'm aware, I'm at least not on the G scanner, which I'm more familiar with. I'm not aware of any efforts to do that.
Right. And Gehua, maybe you have some additional insights?
Oh, I was just wondering if that would be related to proprietary information. Like, is that an allowed thing from the point of view of the vendors?
Right. I honestly, I don't know. I mean, I expect that as long as it's really difficult to get access to a sequence like that, it might not be looked up from the vendors. On the other hand, those that do have access to IDEA or to Epic, they could just try it. Making it public might be an issue. I think that's very serious. But just kind of, trying it and seeing whether it works. I imagine it's a very similar process to what PulseSeq is doing in the other direction. This leads into the second question from Daniel, which is, can we talk about pulse sequence standard? Pulse sequence standard. So I guess, Daniel, the way I'm interpreting it, just like we have the MRD standard or the BID standard for data, can we have a pulse sequence standard?
Yeah, I mean, I guess I feel that PulseSeq is our best sort of effort right now to define a standard. I mean, it may be that as more users pick it up, we might find that it needs to be tweaked here and there, depending on the use cases. But sort of in my mind, I think PulseSeq is essentially designed to be a standard. It's completely vendor agnostic. I mean, I should say that the way that we're completely separating the sequence specification from the implementation or the use of it or the application, it does it limits us somewhat. Like it doesn't, we don't specify how or it doesn't directly support things like slice planning or more sort of interactive use. And so that's an aspect that I think we'll hear more about later, and I think that's a very valid sort of thing to be thinking about. But I think as a standard, having a simple sort of unique way to specify a pulse sequence that can then be ported to various use cases and applications in a robust kind of in a robust way, I think is extremely useful. And so I think as such, I think there will be, I hope PulseSeq will continue to serve that role. It maybe with a few tweaks in the future, we'll see.
Yeah. And
anyway, that's my take on that.
It's a very good moment to be asking this question because the ISMRM is about to start a new committee, and it's kind of in the beginning phase. But basically, in Toronto, they will announce a committee that will deal with standards and measurements. And I know that Jim Pipe is really excited by this potential for adopting PulseSeq as a global pulse sequence standard. I think it would make a lot of sense. And I feel some pressure from this group would go a long way. So just be sure that when this committee is announced in Toronto in May, we bring it up. I think it will be one of the kind of low-hanging fruits that this committee can do because PulseSeq has already kind of done the work. Other comments, questions about this? There's a couple of questions. Sorry, they just started arriving, so I'm going to try to read them and go by the upvote. So please, if you can upvote them, that would help me a lot. I think Lionel asked a question that Jon-Fredrik already kind of touched on, which is what do we do about triggers and anything that's kind of real-time input-output interaction with the scanner?
Sure. I mean, like things like cardiac triggers or like TTL out triggers, that can certainly be supported, and that is supported, at least in TOP and I believe in PulseSeq as well. And things like like perspective gating is not going to be easily supported. So I think that's where other maybe complementary approaches are needed. I think, yeah, there are going to be use cases that are not, at least at the moment, supported by this approach. I think that's kind of inevitable. So, I think hopefully, I think the PulseSeq effort hopefully will sort of be the seed, I think, that can cover, I think, a lot of use cases, and then beyond that, let's put our heads together and see where the need is, see what we can do.
Yeah, thank you. So I'll jump in with a question. So first, the second part of the talk, we'll hear about what Agah is doing for this kind of real-time interaction with the scanner. I would like to just ask a question that's a little bit more specific about the data that Gehua showed, which is you were trying to measure T1, T2, you apply the RSC, the TSC sequence. And I'm curious whether in that comparison of the T1 maps, you only ran it through PulseSeq, or did you also try it native? Because you showed a very high correlation with the T1 values, right, from the phantoms. But I'm curious whether there was any difference between the vendor-agnostic and the vendor-native implementation.
We did not do the vendor-native version because I guess the standard would be having a T1 mapping or T2 mapping sequence, and compared to that, and we didn't have access to those. But
Okay.
that's a great suggestion.
And what about the difference in SNR? I couldn't read the table very carefully, but looks like there was a very big difference in the TSC, but in the vendor native and the vendor neutral implementation.
Yeah, in fact, we've been having some issues with the 180 pulse. And that seems to show up more in TSC, which uses more of them.
Got it.
Yeah, been doing some RF simulation through our virtual scanner platform in order to optimize those pulses.
Perfect.
So, yeah.
Thank you very much. So a question from Penny. What is the impact, if any, on the ease and speed of image reconstruction?
Of using like PulseSeq? Or
right, yeah, as opposed to the native recon.
So one of the things that we'd like to do in the R01 in particular is to see if we can integrate this with the vendor's online reconstruction. So I believe it's called Fire on the Siemens side, and on the GE side it's called Orchestra, and I think that should be not that different, I think, from sequences programmed in the native languages. Like, we should be able to, get the raw data and then use that, the sort of the flexible reconstruction framework that the vendors already have. So we're kind of lucky in that regard, that at least as far as GE and Siemens, I know GE relatively well, that they have kind of sort of opened up the reconstruction framework and allowed users to develop, reconstruction, plugins basically. So it's quite flexible in that regard. So I think it operates. The interoperability is pretty good, I think, with the vendor, because you would need to do that. It's not quite as straightforward. So when you program a vendor sequence now, you can just use the reconstruction directly without any additional work. Like, if you feed in 2D Cartesian data, you'll get an image. So it does require a few more steps, but I think the machinery is already there. We just haven't, it depends on obviously the application, if the application calls for it. So, for example, one of the things we're working on is MP-RAGE. So we have an MP-RAGE implementation that works across Siemens and GE. We haven't, so far we're doing the reconstruction offline, but we'd like to have that done offline. And this fairly standard reconstruction, but it would need to be implemented on using the vendor kind of image reconstruction development environment. So I think the prospects are pretty good for that.
I wonder if it would be helpful to have an open source reconstruction header format attached to PulseSeq that you co-generate with it, so that then it could be fed or translated after translation, be fed into one of the open source reconstruction frameworks.
Mm-hmm. Yeah, that could well be. So I know that PulseSeq already has a feature where it loads from the PulseSeq file. It generates the case-based trajectory. So there's a little bit of that already, but yeah, I think that's.
Yeah.
I think something in that direction. I think it definitely is doable.
Perfect, thank you. And Ricardo asked a question about sequences that are highly looped. I guess sequences that go through many iterations, such as B-values, for example, in diffusion weighted MRI. How easy are they to implement? What are the challenges?
So they're straightforward. So in both of the frameworks that I talked about, everything is just a sequential execution of something. So there's no, there's the PulseSeq file doesn't have any knowledge about loops. So in that sense, it's straightforward. So you would have to, of course, on the reconstruction side, you would need to know, what frames of data to pull out to reconstruct what features of the image, of course. But you have all that information when you design the sequence. So there's no intrinsic difficulty there. There's at some point you probably run out of memory for very long scans. We run functional MRI scans of several minutes, so we've done that and no issue. But there may be an issue at some limit that we don't know about yet potentially. But conceptually, the PulseSeq file basically flattens all the loops. So the loops only exist in the pulse sequence designer's mind. You just have to recall that when you use the data.
We did had some issues running a high resolution 3D radio sequence because it just took too long. It seems not proportionally too long to read it, the PulseSeq file itself.
Mm-hmm.
And also, if there are too many ADC lines, it also seemed to not be able to be read.
Great. Thank you. So I think we're ready to move on to the second part of this session. And first, we'll get a presentation from Agah from Polytechnique Montreal, from my lab, about improving inter-vendor reproducibility of quantitative MRI. And Agah is in Malta at the moment, so I know he had some internet issues, but I think it's going to work out fine. Agah, can you hear us?
Yeah, I can hear, but it just disconnects every now and then, and I'll try to rejoin in that case. Sorry about that.
The moment you disconnect, I'll DM you, and you'll be aware.
Okay, let me share my screen.
So please go ahead.
Okay, I guess my screen has been shared.
Yep, it's good.
Okay, thank you. Thank you so much. So, yeah. Hi, everyone. I'm Agah Karakuzu, a postdoctoral researcher at Polytechnique Montreal. And today I'll talk about how vendor neutrality and open source implementations can improve inter-vendor reproducibility of quantitative MRI. I'd like to start my presentation with a screenshot from the operator manual of a 3T CMAS scanner. It says, "This is not a measurement device. Measured values obtained are only informational, not for diagnostic purposes." And when we go to the reference standard, we see the reason why. A measurement must quantify a physical parameter, but this is not what manufacturers aim at. Because clinical use of MRI is dominated by weighted imaging, so vendors strive for faster acquisitions and better image quality, then measure their success by increasing efficiency and diagnostic performance. But when it's about MRI measurements, as researchers, we try for sophisticated models and interesting findings. Then we measure our success with the number of prestigious citations and grants. And this means a lot of round trips between scanners and papers. But at some point, we expect to see quantitative MRI in clinical use, and the key to open a portal between research and clinics for MRI measurements is independent replication. But what could quantitative MRI achieve if independent replication was granted? Here's an example. We are looking at 3 hyperintense MS-related lesions on a conventional MR image, where we cannot distinguish between demyelinated and inflammatory lesions. And this is a quantitative map of G ratio of the same patient. The normative can set a threshold of 0.8 to support the demyelination, which will appear in hot colors here. And side by side, you can see only one of them shows the demyelination. So this could be a big added value if we could easily deploy this method across imaging centers and standardize the quantification. And this is a longitudinal follow-up of MS patients using a much simpler metric, T1. Changes are within an 8% range, and the significant maps highlight some of these regions. And the study reports that conventional contrast didn't indicate a notable change. So quantitative parameters here capture something that weighted images cannot. And such findings are valuable when our minimum detectable change for T1 is lower than 4% in this case. So whether we are talking about the G ratio threshold at 0.8 or a 4% change in T1, we need sensitive and specific quantitative MRI biomarkers. And speaking of sensitivity, when we look at the literature on the relationship between T1 and myelin histology, prediction interval R-square ranges from 0.07 to 0.99 with an estimate of 0.53 on average. And then similar numbers we get for yet another relaxometric parameter, which is T2, and other metrics of MT and diffusion. You can take a closer look at the interactive version of this analysis on neurolibra.org and reproduce these numbers. But in a nutshell, what we see here is that almost all these quantitative MRI biomarkers are statistically equivalent in myelin imaging. And this points to a profound variability in quantitative MRI experiments. So to solve this problem, we need to standardize MRI measurement workflows, which all share these 3 main components: acquisition, reconstruction, and downstream processes that follow. And we can define 3 benchmarks for them. The first one would be a black box where all 3 components are proprietary. We can only change some acquisition parameters and observe the changes in the output. And when we open up post-processing, then we define gray box workflows, but we still don't know the details about the acquisition and reconstruction. And in case of a glass box measurement workflow, all 3 components are transparent and also editable. This gives us full control of variables that affect our measurements. But going from left to right, simplicity of execution decreases as we are increasing the number of external dependencies. So if we want MRI measurements in clinics, we need glass box workflows that are also user-friendly. And to achieve this, at the post-processing level, I developed qMRI Lab, qMRI Flow, and quantitative MRI bits. For data acquisition and reconstruction, we worked on qMRI PulseSec, then combined these tools to test the effect of end-to-end standardization on measurement stability. And finally, for reproducible publications, we are working on Neurolibra. So, can you still hear me, Nicola?
Yes, it's all good. You're here.
Okay, cool. Okay, I'll ask every now and then. So these are the main components of a quantitative measurement. We have file collections acquired by varying a set of imaging parameters between multiple scans. Then we use optimization algorithms to fit that data to a model and obtain parametric maps, such as a T1 map, M0 map, or a field map. To standardize models and parameter fittings algorithms under one umbrella, we developed qMRI Lab, which is quantitative MRI under one umbrella. And under that umbrella, we have a collaborative MATLAB code base that makes it easy to get available tools in a modular open source framework. So far, this attracted more than 20 collaborators and made qMRI Lab one of the most popular quantitative MRI repositories on GitHub with about 100 stargazers. You can use it for running simulations, fitting data, and performing sensitivity analysis of your quantitative MRI protocol. And we have several interfaces available. We cover more than 24 quantitative MRI methods from a variety of measurements. And to make it easy, we make it easy to integrate qMRI with compute platforms. But when qMRI Lab started, there were 45 open source packages for quantitative MRI. But as of today, there are at least 13. And these are developed in a variety of languages with different applications in mind. And this made me think again, how can I bring quantitative MRI under one umbrella? And obviously here we need interoperability, which happens when there is a common language. And proved by the last 6-7 years, the language we need is the brain imaging data structure. That's why we developed a BITS extension for quantitative MRI, where we standardized data and metadata specs for more than 15 quantitative MRI methods, standardized units and definitions for 18 parametric maps, and made sure that the distinction between conventional and quantitative use cases are clear by introducing a new common principle named file collections, and we provided example datasets and applications. For example, in qMRI Lab, without BITS, it takes at least 11 lines to load the data, set the protocol, fit the data, and to save the results. But with BITS, it is just 3 lines with the same entry point across models, and the output follows a community data standard, which comes with all these advantages out of the box. But again, fitting data and post-processing is just one step among many others. If we were to imagine a neuroimaging study as a planet, then we create a planet per research, a paper. And in the end, each paper is a world of its own, and all of them have multiple layers. On the surface, we have statistical analysis and data visualization. If we can make this layer transparent by publishing integrated research objects, then we see the next layer, which is processing. And thanks to open source tools, we can make this layer transparent as well, which would reveal quality control to trace back issues rising to the surface back to their origin, which is image reconstruction. And we all know that there are powerful open source solutions for reproducible reconstruction tasks as well. But this end-to-end transparency comes at the cost of an increasing number of dependencies. Then the question would be, what holds a paper together so that we can easily navigate between these visible layers? And my answer to that is data standards and reproducible execution environments combined in a data-driven workflow. And to implement this, from scanner to publishing integrated research objects, I developed qMRI Flow, which are data-driven and container-mediated quantitative MRI pipelines powered by Nextflow. Can you still hear me?
Yes, all good, Agah. Sorry, couldn't
Okay.
quick enough.
So here's an example qMRI Flow. We are starting with the conversion of case-space data into MRD, and then we call gadget run in its own container to perform the reconstruction, and then converting that data into bits. This is followed by motion correction by using elastics, and then we pass the derivative data, which is motion corrected between different scans, to qMRI Lab for performing quantitative processing. I think one useful approach is that you can change any of these components at whichever step you want, either by locally installing a dependency or just by pulling another container. So the workflow logic will remain the same thanks to our data standards. And then this is a simple summary of what qMRI Flow is. It's MRD, bits, a lot of containers in a Nextflow pipeline with qMRI Lab. But up to this point, the core layer of a paper was hidden in the background, which is data acquisition. And to make this layer transparent for standardized quantitative MRI acquisitions, we developed qMRI PulseSec, which are MRI pulse sequences that you can download from GitHub to your GE or CMS scanner and run them to acquire your experimental data. Now, finally, when we combine qMRI PulseSec with qMRI Flow, we go from papers to a planet where quantitative MRI is standardized, which is Venus, which stands for vendor-neutral sequences. With Venus, we are trying to solve a 3T problem First, to bring transparency to all the elements of the pulse sequence implementations, and then to play identical pulse sequences on scanners from different vendors using the same operating system. And we aim at developing user-friendly quantitative MRI protocols. And we achieve this by combining our open source solution with RT-Hawk real-time imaging platform by a company named HeartVista. And this platform is approved by FDA for clinical use on Siemens and GE scanners. But why unifying sequence executions is important for measurement reliability? Because these pulse sequences often look easy on the paper, but there are a lot of decisions to be made in the background for implementing them. For example, in this case, for the MT pulse, the duration between the MT pulse and the excitation pulse itself, along with RF spoiling rules, then the 3D readout module, the spoiler gradient, and some higher level implementation details, such as how pre-scan will be managed across quantitative MRI scans, all those iterations. And those pre-scans make yet another important factor for the accuracy of quantitative MRI acquisitions. So of all these options, I'll talk about the influence of just one of them to the accuracy of T1 quantification, which is RF spoiling. Commercial SPGR implementations of major vendors do not agree on a single value, and there is quite a bit of literature on the use of different values for T1 mapping. For example, this study by Yarnik shows the dependency of T1 measurement on the phase increment. You can see how T1 estimations fluctuate depending on the selected value. And on the second figure, we see that the value 117 yields the lowest error for a range of T1 over T2 values, which is not either of the choices vendors make. And of course, there are many other reports on this issue for different quantitative MRI applications, and some recent studies developed vendor-neutral sequences and performed quantitative MRI, but they were mostly within vendor. And the effect of vendor-neutral approach on inter-vendor variability was an open question. And to test this, we developed a vendor-neutral 3D SPGR sequence for magnetization transfer saturation index imaging, which gives T1, MTR, and MT-set maps. And then we scanned the ISMR-MNIST system phantom and 3 healthy participants on 1 GE and 2 Siemens 3 Tesla clinical scanners, first using a vendor-native MT-set protocol. We equalized the acquisition parameters between scanners as much as possible, but of course, there were some inevitable vendor-specific differences between GE and Siemens. Then we deployed our vendor-neutral MT-set implementation on these scanners, where all the acquisition parameters were identical. And with Venus, we have the same control interface for different scanners, where the images are exported in bids instead of vendor-native DICOM files. These are the GE and Siemens Prisma scanners from the imaging site in Toronto. They are labeled as G1 and S1 native or Venus, depending on the implementation type. And this is the 3T Skyra scanner, our development site at the Montreal Heart Institute, which is labeled by S2. So these are the results from the Phantom, where open cross markers here indicate the reference values from the T1 plate. And our results indicate up to 12% improvement in accuracy with the vendor-neutral implementation, as well as a reduction of inter-vendor variability for T1 values between 0.4 to 2 seconds, which is the relevant range for brain imaging at 3 Tesla. And in vivo vendor-native results show a bias between Siemens and GE scanners. You can see that GE values are consistently higher than the Siemens ones, but with Venus, we remove this variability at its source so that the measurements can be independently replicated on GE and Siemens scanners. And this is also evident by between scanner coefficient of variance. It decreases for each participant and across participants when we use glass box Venus workflows instead of gray box workflows that start with a vendor native acquisition and followed by an open source post-processing. And this trend is consistent for all metrics and participants.
All right, so Agah cut off. It did happen eventually. I just sent him a note, so we're gonna wait a little bit. I think he's just gonna refresh and hopefully we'll be back. In the meantime, feel free to send questions in the chat window or in the Q&A window. And also, if you have any questions about this is the one presentation on which I can answer pretty well. So feel free to start a discussion while we're waiting for Agah. Yeah, so a question from Lionel. It looks great, but also intimidating. How much effort is needed to use the entire qMR flow toolchain if we developed a completely new pulse sequence? It depends on what you need. I mean, in the end, these workflows are done by Siemens. They're also done by researchers in-house. So, hi, Agah. I was just entertaining while you were out. Lionel, maybe we can get to that question after Agah finishes.
Okay. Can you tell me on which slide I was when it cut off?
So you showed the whole after the coefficient of variance, the
shift functions.
cycle.
I get. Okay. Let me share my screen again and.
Yeah, the shift analysis is where you cut off.
I can see if I'm sharing my screen.
We don't see anything right now.
Just a second. Sorry, I just need to refresh the page.
Yeah, that's okay. So I'll continue with answering Lionel. So if you have a completely new pulse sequence, generating, depends on where you built it. If you built it in pulse, in SpinBench or any of the vendor neutral protocols, we actually have a connection to qMR Lab, which is our post-processing tool. So if you deployed a sequence on SpinBench, it will execute on the scanner. The data will be reconstructed using either the native reconstruction or Gadgetron, and then you would be able to process everything with qMR Lab. Agah, we can see the slide now. Can you hear us? Well, now we can see the slide, but we can't see Agah. Maybe third time we'll be lucky. Okay, looks like he disappeared once again, so let's wait. Third time is the charm. And so there is a question from Jon-Fredrik about the vendor differences in the T1 mapping sequence that was overcome by Venus. Our suggestion is that this is all related to pre-scan. And in particular, we noticed that the transmit gain is very different between scanners. And we were very lucky that there was a scanner upgrade, XA30, that actually showed how variable the pre-scan transmit gains are between two different software versions on the same scanner. So that transmit gain translates into B1 inaccuracies. And then there's also the spoiling issue that Agah presented. So we think that it's a combination of those two.
Yeah. Can you hear me now, Nicola?
Yes, but I can't see your screen, so
I will share my screen. I just want to make sure before that you can see me, and maybe I can get to the questions later because I see some questions here. But let me try to finish the presentation first. Hopefully, few more slides.
You almost made it. You're pretty close, but
almost the terrible Wi-Fi connection. So sorry. Okay, I guess now you can see the screen, and also here you can hear me at the same time.
Yeah, exactly.
Beautiful. So yeah, I was just trying to say, when we look at all the metrics from all the comparisons, we see a consistent trend going from vendor native to vendor neutral. Between scan differences are reduced. In this particular case, it points to a 23% bias reduction And we also see the trend of the differences across the distribution ranges also changes from a nonlinear trend to a bit more uniform differences. And this has some implications, and it shows why standardization at the measurement source is more effective than harmonization on high-order derivatives. So with Venus, we confirmed the hypothesis that vendor-neutral and open-source implementations decrease inter-vendor variability of T1, MTR, and MT-set measurements. And you can reproduce this study at qMRlab.org/Venus. And what's next with these vendor-neutral platforms? Well, one thing we'd like to achieve is to collaborate between other vendor-neutral developers who are on this call with us today, Pulsec and GammaStar, hopefully through this Chan Zuckerberg grant that we recently submitted. And then we also expect to explore the benefits of vendor neutrality for AI-driven applications. And we are also working on the integration of Spinal Cord Toolbox, which is another software from our lab, with Venus. And we already have some promising results to achieve accurate spinal cord cross-sectional area measurements. Can you still hear me?
Yes, all good.
Okay. So to explain quantitative MRI, qMRI lab ecosystem in a nutshell, traditional approach to quantitative MRI is a hurdle race, and we need to jump over many proprietary roadblocks to run a quantitative study to publish a paper. With our open source and vendor neutral solutions, we can remove these hurdles in the way of quantitative MRI, so it becomes a sprint race. This way, we can not only reach the target easily, but we can follow each one of these steps back to their source for reproducible quantitative MRI, from scanner to publication of integrated research objects. And why integrated research objects? As you all know, traditional publishing can only offer PDFs, but with today's technology, we can combine runtime, code, text, and data to publish reproducible papers so that everything is reproducible from paper to scanner. And this is the main mission of NeuroLibre, a preprint server for reproducible analysis. You can visit our page at neurolibre.org. And before I finish, I'd like to make a quick announcement about a marathon, which is a hackathon for MRI professionals. We organized the first one in 2019 in Montreal before the ISMR annual meeting, but unfortunately we couldn't follow up for the next years because of COVID. But hopefully this year, our plan is to organize a marathon after the ISMR annual meeting in Toronto. You can follow up the updates on our website, marathon.github.io. So if you're interested in participating, please send me an email, agahkarakuzu@gmail.com, or you can send me a DM on Twitter as well. My handle is Agah Karakuzu. And with this final note, I'd like to thank all these funding organizations and my colleagues at the Neuropoly Research Lab. Thank you so much, and so sorry for all these interruptions.
Thank you very much, Agah. We'll wrap up with a presentation from Nora Breutigam. She's at the Fraunhofer in Germany, and she will talk to us about from static to dynamic, the evolution of vendor-independent MRI frameworks. Nora, can you hear us, see us?
Yeah, thank you very much for the introduction. I will try to share my screen now. See if this works.
That's perfect. We can see it.
Yeah, you can see everything. Perfect. Yeah. So yeah, I'm Nora Breutigam. I'm from the Fraunhofer in Bremen, Germany, and I've really enjoyed listening to the other talks. So thank you very much for the nice visuals, Agah. And in my talk, I will introduce the evolution from static to dynamic imaging in vendor-independent MRI frameworks. So first, I will give some short motivation and show a few examples. And then I will introduce real-time capable vendor-independent frameworks. And because I'm working at Fraunhofer and we have an ongoing development of our own framework called GammaStar, I will dig a little bit deeper into there and also give you more technical details of how we deal with real-time applications. So yeah, if you have a normal structural imaging sequence you export from your framework, and you go to the scanner and you only want to change the field of view or your imaging protocol parameters like TR, TE, echo spacing, and so on, you're totally fine. But as soon as you have more advanced imaging techniques like cardiac MRI, where you have to trigger something in real time, or you have a physiological imaging technique like perfusion imaging, where your underlying physics of your patients are very different, and you want to adapt for this in your sequence, or you want to correct for motion during your scan and not afterwards, then you have more advanced imaging techniques. And for that, you also need more advanced vendor-independent sequences. So let's have a look at a very simple dynamic correction of subject motion. So if you have a subject laying very still in the scanner and only involuntarily move a little bit, you end up with almost motion artifact-free images. But if you have a patient, sorry, does it work? No, usually the head would move a lot around. So if you have a patient that moves a lot around in the scanner, you end up with very motion corrupted images. So one solution for that would be to follow this motion with your imaging plane. And if you do that, you end up with very nice motion artifact-free images despite the motion. But for that, you have to be able to adapt your sequence during the runtime of your measurement. And the same is true for timing changes in real time. So let's have a look at these perfusion-weighted images. And the underlying sequence has a certain inflow time, which allows the blood to flow from a certain imaging plane, a labeling plane where you label or mark your blood, to flow to the brain. And for one patient, you end up with a very nicely fully perfused brain. But in other patients, for example, if you have delayed perfusion, you end up with a different stage. So one solution would be to adapt this inflow time in your sequence according to the physique of your patient. And then you could end up with almost the same images, so very nicely perfused brain, but with different imaging timing. And for perfusion-weighted imaging, the background suppression is also very important. So you want to suppress static tissue with certain T1 relaxation times. And these T1 relaxation times are always in a certain range in the brain, but the exact numbers are highly individual. So for one patient, the timing of background suppression pulses might be perfect like this. And for the other patient, the timing like this would be a little bit better. So in both cases, it would be great to be able to react on further images or images in your reconstruction and then adapt the sequence on the fly so that you don't unnecessarily prolong your overall measurement time. So let's have a look at a few examples of vendor-independent frameworks. We've heard a lot about PulseSec already. And I just wanted to present shortly PulseSec X-Phase to you, which was presented at the ISMM last year. And this allows prospective motion correction by using an external tracking hardware device. It's an optical tracking system. You have a mouthpiece in the subject, and this tracks the motion. And PulseSec is now able to adapt or update the sequence at multiple temporal positions, here indicated with these arrows. So in case of prospective motion correction, you would then adapt the sequence right before the IF pulses here with the blue arrows. But in principle, other positions are also possible or thinkable. And we also have I've heard a lot about Hardvista, or the RT-Hawk research platform by the company Hardvista already, that runs on GE and Siemens systems. And in the beginning, it really focused on cardiac MRI. So it had to be able to have this real-time imaging and also allow the communication between the reconstruction side and then trigger changes in the application that runs on the scanner PC. So it allows these incorporation of real-time data from external hardware as well, which allows then interactive scanning, triggering, gating, and also device tracking. So it's very powerful already. But because I'm not working with PulseSec and also not at RT-Hawk or Hardvista, but at Fraunhofer MIBIS, I will present GammaStar in a little bit more detail to you now. So GammaStar was developed a couple of years ago, or the development started a couple of years ago, with the aim to have a very intuitive way to develop sequences in a modular fashion and to accelerate these development of sequences in a web front end. And also we wanted to be able to run the sequences with a translator. We call these translator GammaStar driver to all the different vendor systems and also software versions of one vendor. So if you want to try out the web front end, it's an offline and limited version published already. You can just Google GammaStar and Fraunhofer Mivis together, and you will end up at this page. And there's a nice feature. You can maybe give your volunteers a heads up how your MR sequence will sound in the scanner, and yeah, just play around a little bit with that. So how is the GammaStar sequence structured? We really wanted to rethink how a sequence is built. So GammaStar sequences are built in a hierarchical sequence tree structure where you define child relations and also the loop structures in there. And each of these sequence elements holds a bunch of parameters defined in Lua code. And Lua is a very flexible programming language that we are using in GammaStar right now. If you're now stepping through this sequence tree structure, calculations are triggered that build these normal sequence hardware events you're all familiar with. So the RF pulses, different phase encoding gradients, and so on. So what's special about GammaStar is that we take this logic, this whole GammaStar tree to the scanner and keep the flexibility that comes with it. So we have this scanner-independent GammaStar sequence tree structure exported from our web front end. And this goes then to the scanner-independent GammaStar backend that is also located on the scanner PC. And this GammaStar backend interprets the sequence, and this goes both ways, and streams then the hardware events to the scanner-specific GammaStar drivers. And this communication is also not one-sided, but both two-sided. So we can configure the GammaStar sequence. We can adapt the field of view, the number of slices, the slice position, and also all these protocol parameters like TR and TE at the scanner. And we would like to show you a short video where you can get a feel how GammaStar works on a Siemens system. But because the audio does not work here, I would just quickly end my presentation and to the video. Go to the video. So I believe I just have to click here and share a video link. Let's try that out. Sorry. Here's the link. Copy the link. Okay, share. Let's see if this works. Let's buffer. Okay, so now you see the normal UI of our Siemens system at our institute, and we can then load the GammaStar sequence here and just start the sequence. For the video purposes, we choose a very short 2D flash sequence with only one slice. So sequence the normal, like a normal research or product sequence, and start the sequence. For purposes of this video, we skipped advanced chimming, so we only have a very short chimming process up front, and then you're also able to reconstruct the images right on the scanner and use the UI to go through these slices. So in the UI of the scanner, you can also change the position of the slice and the field of view, and then run the sequence again and have another slice of the water-based engine. Just have to let the video buffer a little bit because of the size. So yeah. then you'll see the other slides. So if you want to change now the sequence protocol parameters, you can open another UI from GammaStar. And within the UI, you are able to adapt all these different sequence protocol parameters you are familiar with. So for the video, we just increase the number of slices here. And then we also have to adapt TR accordingly. Okay, and then we will acquire more slices again. In the UI of the vendor, you also see how much time your sequence takes. So the acquisition time is also visible, and then you can again look at the images you acquired. So if you want to change the GammaStar sequence, you can again click this change sequence protocol, and then you can select all these different GammaStar sequences in our library. And for the video, we choose a pulsed to spin labeling sequence, which is kind of a more advanced sequence. And this is used for perfusion-rated imaging without contrast agents. The video buffer again, and then we can listen to the sequence. Because perfusion doesn't make so much sense in a water-based phantom, in the end you will see only the label or control images. Yeah, so in principle, also longer sequences are possible with GammaStar. Just for the video, I don't want to show you the sequence that takes several minutes. So let it buffer again, and then start the sequence. Yeah, so now you listen to the typical ASR sequence sounds. If you've heard them once, you will never forget them. And then, yeah, we will see the results shortly, and then I will go back to my presentation. All right, so then let me see how I can go back to my presentation again. Share. Okay, so with GammaStar, we wanted to take it a step further. We didn't want to change only the field of view or the sequence parameters at the scanner, but we also wanted to have a communication between the scanner and our backend. So our GammaStar backend is really a real-time backend now, and it allows complex changes during runtime because we're able to provide this feedback. And for that, we had to change the calculation of our sequence. So if you have a static sequence, you pre-calculate everything prior to your scanning. But if you want to be able to incorporate feedback, you have to have a real-time sequence execution. So without the feedback option, you can randomly step through this GammaStar tree structure and calculate your sequence elements. But then you are not flexible anymore because you have pre-calculated everything and you cannot change everything that lies in the future. So we had to have a more intelligent way to go or step through this sequence tree. And so now we are traversing it in a more chronological order, so that we only have to buffer in the close future, so only in the near future, and everything that lies here in the future is not calculated, so we can then adapt that during scan time and reconstruction. This not only allows sequence changes on the fly, but also it allows long acquisition times and complex sequence structures because we don't have this massive amount of data pre-calculated. GammaStar is not only able to communicate with the vendor reconstruction software on the scanner, but we incorporated a WebSocket server here. And this is also located on the scanner PC. So it looks a little bit external here, but it really is included into the scanner in the scanner backend. So with this WebSocket server, we are able to apply any arbitrary sequence changes, and only the relevant calculations are then triggered. So for instance, if you want to apply this motion correction with the adaptation of the imaging plane, you could use your raw data from your scanner, send this to Getritron, an open reconstruction software, use ITK and calculate your motion information and send this to this WebSocket server, and then calculate your updated imaging plane, and the whole process is then triggered, and send this to this GammaStar driver again and start the sequence with updated parameters. Another example would be wire tracking by using the software Mebus Lab and OpenIGT link. And wire tracking is important for interventional MRI. If you want to track wire through vessel, for instance, you can either use CT or an X-ray, but as an alternative, you can also use MRI. And with MRI, you have to use a passive MR tracking system here, so that you are able to see a signal difference of the wire. And then you can track the signal differences with Mebus Lab and follow the motion of the wire while it goes through this vessel, and update your imaging plane accordingly, so that your surgeon always sees the wire and the location in the 3D vessel. So further applications also thinkable, and I've explained or presented already a few of them. So you have this capability now to real-time adaptation of your imaging timings. You can also have external triggering of your sequence events. You can, for example, correct for B-field drifts with a frequency correction, and also have a synchronized control of your external devices with metamaterials, for example, and a few more. So you're quite flexible with GammaStar. And that's from GammaStar for now, from my side. If you have questions, just send us an email or ask in the Q&A. And at the end, I would like to say a few words about open science and what these vendor-independent frameworks means for that. So I really believe that with our vendor-independent frameworks, we can break these borders we have with the different software versions or different vendor systems. If one research group has implemented a sequence and another research group wants to re-implement the sequence or further develop it, you often have to re-implement the whole sequence, and still you cannot be sure that you have comparable results in the end. So a coverage of all these different MRI vendors by our vendor-independent frameworks, which were presented today, would be very desirable. And also a collaboration between the different frameworks to really have a better compatibility and don't build new borders, right? So yeah, last but not least, if you are thinking and talking about open sequences, you always have to think about open image reconstruction softwares as well, and how they too communicate with each other, so that you have really an image harmonization and a comparability in the end. So yeah, let's open up science, and thank you very much for your attention, and I'm looking forward to your questions now.
Great, thank you, Nora. And I think we have about 10 minutes for questions. And I guess the questions will focus on the last two talks, but if anybody wants to join from the previous session, give their opinion, I feel that the more the merrier. And please put your questions in the chat window or the question window and upvote the questions. So I see that Agah already answered some of the questions in comments. And maybe we can just continue with a more general question, which is how can we create these flows? Like basically, what is necessary so that we can create these transparent, reproducible workflows? And maybe Agah can put it in the context of Venus and that project, but also I'd be curious, whether Nora has used any other tools that are kind of container-mediated, data-driven, to make it easier to execute certain analysis. So Agah? And I see you, but looks
I think
like
he's frozen again.
doesn't seem
I'm not
frozen.
sure.
I think he's moving. Or
I'm not sure. I think he.
too much.
Yeah.
Nora, please feel free to take over.
So I personally have already used this qMRI lab for analyzing my data. But with GammaStar, we are really focusing on the imaging side right now. But in principle, every communication is possible via our WebSocket server. So yeah, Gadgetron is one software solution for that, and then you can go further. And we are also are able to have these MRD format, which you can then use in every other software.
Thank you. Here you are. We hear you.
Yeah, okay.
Workflows, how generalizable are they? You know, like how easy is it to get other sequences to use them, and how can we make everything data-driven, containerized?
Is that for me now? How?
So Nora already gave an answer, so yeah, it's for you.
I mean, within the platform that I worked on, RTHawk is pretty flexible, and it also has really good considerations about the hardware and patient safety. So given all these existing tools and libraries, it's possible to develop different kind of sequences. And as long as we have a reconstruction task planned, as the workstation in this case is independent from the vendor workstation, it's pretty flexible to run any kind of performative tasks you'd like to achieve. It's limited by your computational power on your workstation in that case. But yeah, it's maybe if real-time reconstruction is of concern, of course, you don't want to defer that task to containers because there will be some latency, but it's possible to open a port, stream that data, and do fast calculations that way. But yeah, depending on the need, can be flexible with or without containers.
So this is a question from the previous session, but I think it is relevant for you two as well. How do you deal with any kind of input-output interaction with the scanner? So the question from Lionel was about triggers, but it could also be with setting up a protocol, acquisition parameters in real time, and any of those challenges.
I think this question would be perfect for Daniel because he's one of the main developers. Maybe Daniel can also join the stage or answer for me in the chat. And so go ahead, Agah.
Yeah. I mean, I also don't want to appear like I'm advertising RTHawk too much, but it's possible on that platform to associate your sequences with any kind of input trigger or do any device tracking or cardiac gating, which is the main purpose of this.
There was an echo, so I think it's because Daniel is joining. So Agah, you can.
I was joining. Okay. So yeah, on that end, it's all manageable and open for modifications.
Yeah, Daniel.
Okay, so basically we have two different solutions. So first of all, because we use this Lua programming language for building our sequences, there's a very easy Lua C API. So basically all the render sequences are written in C or C++. And so we have a very direct connection between the sequence and the Lua backend. And so protocol parameters and all the bi-directional communication between QMStar backend and the driver is quite easy by using Lua as programming language, which is then statically compiled or linked into the driver sequence. And the other things I think Noah already showed. We use WebSocket servers for communicating with external devices, for getting trigger points, and doing real-time interactions with the sequence.
Great, thank you. And Daniel, you had a question in the chat, so maybe you can ask it person.
Yes, I got a question for you. So there was one slide, something in a nutshell. I think qMRI lab in a nutshell, and there was still one hurdle standing in the end.
Yes.
Was it on purpose?
Yeah.
And which one was it?
It's publication.
I just didn't remember which one it was. Okay.
Yeah, that was the publication. I guess the constant hurdle. Yeah.
Yeah. I mean, we can get away from it and just put a preprint up and be done with it. But yeah, otherwise we would still need to jump it.
Would be running.
I got cut off again, but yeah, maybe we should just kind of run through it and not jump it. Let me just tell him that he's off again. And let me take a look at some of the other questions. Yeah, so I would be curious about this call from Nora about opening up science and harmonization. As we've heard many times, solutions are 20% technical and 80% social. What do you see as the most important thing at the moment? What should we be doing? Here we are on the call. It's probably the first time that 3 vendor-neutral platforms are together. What do you think would be a good next step, social or technical?
So I think social-wise, we are already very on one level. So we are not talking for the first time with each other today. So I think social-wise, we are very fine. So I think we have really issues with all the coverages of the different vendors and software versions. We are limited right now to achieve that. So yeah, let's see how this progress goes on in the future with also our joint calls. And maybe also collaborating with the open reconstruction software developers as well. I wrote that in the chat or in the Q&A. It would be really great to have these standard export, which all frameworks can then follow up, and these export files are then standardized for all sequences and different vendor systems. That would be awesome, and accelerate research a lot, I believe.
Yeah, I agree. Agah, what would you say is the most important next step?
I guess the results from the next reproducible research group study challenge of ISMRM can maybe help us answer that question better, because I guess if I remember correctly, there is a PulseSec implementation was in the question to implement it across sites, which is definitely, I guess, giving a bit more importance on the social aspects. And I would rather prefer starting with simple sequences and focus on the social aspects first, and then solve the technical problems that comes out of that. And I think the first one is again a social problem for wider adoption.
Yeah, and looks like MP2 Rage is a low-hanging fruit in the sense that there's already implementations. It started out as an open source sequence, became product on Siemens. It's not on GE. We all are aware and capable of implementing it. I think something like that could actually go a long way towards saying, look, we have a unified implementation. We've agreed on the description, and hopefully that gets more widespread adoption. So it's 1 minute to the hour, which means we're just on time. And from what I can see, I don't think there's any questions that weren't answered. Some were answered in comments by Agah, so I think we're clear there. And I would like to thank all of you for joining, ESMRMB for organizing this. And I look forward to the next 2 days when we can hear a lot of other reproducibility and open science solutions to our MRI problems. Thank you once again. And this will be recorded so we can revisit it at a subsequent time. Have a good rest of the day, and I'll see you in the other sessions.
Thank you.